Who are you? What, when, why, where, and what are you? Well, science can answer some of those questions, but cannot answer all. What are you made of? Well, sugar and spice, everything nice. You have your personality, and you have your appearance. Now, your appearance based on your physical traits. Personality is not based on personal traits. So you can use science then to perhaps define what you are physically, but not mentally or not your dreams and so on. How you got here? Well, science can tell you some of the steps, but on some of the fundamental questions, you can't. No, perhaps never will be able to. Why you are here as well? Science can't tell you that. Where you are? Perhaps. And when you got here? Perhaps. But what are you made of? Well, first let's look at your physical makeup. You're made of 80% water. Water is a molecule. And molecules are made up of atoms. Water has 2 hydrogen and 1 oxygen atom. 3 atoms in total. And you're made up totally of atoms. That's your building blocks. You have other atoms, like carbon is important for you because it can combine with other atoms and atoms of other atoms of carbon to form large molecules. Now the atoms are like elements over there, and your elements or atoms can be arranged from the lightest up to the heaviest. Atoms are made up of negatively charged electrons surrounding a nucleus made up of protons and neutrons. And as you go up the periodic table, which lists all your atoms or your elements, from the lightest to the heaviest, you get more protons and neutrons. Normally there's as many electrons as protons as neutrons. The exception being hydrogen, which only has 1 electron and 1 proton. Now, you wanted to go to a meeting, and because you had something important you wanted to say. But when you got there, you were totally ignored, as though you weren't even there. And you weren't even heard or seen. And you were quite angry. You felt like you were almost going to explode. But be careful, don't do it, because you're made up of over 50% hydrogen atoms. And hydrogen is an atom or an element that explodes. They used to use it in the airships, the Hindenburg, and they exploded. So they now have to use helium, the second lightest element, 2 neutrons, 2 protons, and 2 electrons. So keep cool and don't explode. But the size of your nucleus of your atom is to the size of the atom, your atoms, as a speck of dust is to a football field. So you're made up mostly of space. You're virtually nothing at all. Maybe that's why you weren't noticed. You're 99.9999999% space. So why don't you fall through the floor? Because the atoms in the floor are also virtually empty. And the force of gravity is trying to pull you down into the center of the earth. So what's stopping you from going through the floor or going through the earth? Well, your atoms are surrounded by negatively charged electrons. The atoms in the floor are surrounded by negatively charged electrons. Like charges repel. Put a negative charge on 2 pith balls, hang them down by threads, and bring them together, and they try to fly apart. So what's that force called? That keeps you from falling through the floor, or walking through a wall, or pushing your finger through your hand. It's called the electromagnetic force. Let the force be with you. And that stops you from touching really anything, or anything touching you. You, for instance, levitate 1 angstrom unit above the floor, 10 to the minus 10 meters. Now you've had other days too, besides not being recognized as you should be, where you're somewhat depressed or sad. Other days where you're happy or elated. So you have your ups and downs. Physically, you're all up and down. You're made up of up and down quarks. Your proton has 2 up and 1 down, and your neutron has 2 down and 1 up. The up quark, has a positive charge of plus 2/3. The down, negative charge, minus 1/3. So 2 up and 1 down, plus 2/3, plus 2/3, minus 1/3, charge of 1. Proton has a charge of 1. Neutron, 2 down and 1 up, minus 1/3, minus 1/3, plus 2/3, 0. No charge, or 0 charge. You also have days where nothing seems to work. You're frustrated. The more you try, the worse things get. It's like everything's falling apart. You can't hold it together. Well, all of your nucleus of your atoms, except hydrogen, have more than 1 proton. And protons are positively charged. And like charges repel. So what is holding your nucleus of your atoms together? What's holding you together? Why don't they fly apart? Why don't you fly apart? There must be some strong force, and stronger than the electromagnetic force. Stops you from flying apart and holds your nucleus of your atoms together. What's it called? It's called the strong force. Let the force be with you. But as I say, you're made up of over 50% hydrogen. There's over 50% of your atoms are hydrogen. Where did you get those? When did you get those? How did you get those? Well, before the 1920s, no one knew. But then Hubble, looking through the largest telescope on Earth, at the Mount Wilson Observatory in Los Angeles, he saw that all the stars were going away from the Earth. What's that mean? Well, the universe itself must be expanding. Well, what's that mean? Going back in time? It becomes a smaller and smaller and smaller and smaller and smaller place. Until you get down to something the size of a pea. We have all the forces, all the material, your Aunt Mary, everything is in that small space. And then, of course, if you go down, it must be down to time equals 0 when everything is created. And science just cannot answer that question about how you got here and the fundamental basis, because that's when the universe and you came about. And it may never know if it believes its own theories. Because Planck, back in the early 20th century, said that time is discontinuous. What's that mean? Well, it must be the smallest unit of time. You can't keep breaking time down. Like you start at 1 billion years, 1 million years, 1,000 years, 100 years, 10 years, 1 year, 1 month, 1 week, 1 day, 1 hour, 1 minute, 1 second, 1 microsecond, 1 nanosecond, until you get down to 10 to the minus 43 seconds. That's 1 over 10 to the 43. A very small fraction. And you can divide no farther. He called it a quanta of time. And he's one of the founders of quantum mechanics. So if you can't go below one quantum time, how can you ever get to time equals zero? So the science cannot tell you how you got here. They figure that between one Planck time and time equals zero, there's a superforce containing all forces and all. Okay, we have mentioned the three forces, and there's one more. We mentioned the force of gravity, strong force, electromagnetic force. Now, in math, when you try to divide by something smaller, divide by a quarter, you get something 4 times as big. And take it down to try to divide by 0, and all hell breaks loose. You get infinity. And infinity is the largest number you can get. So how can you add anything to infinity? Because it's already the largest number. So math breaks down. It's called a singularity. So time equals 0, that's another singularity. So is there something infinite there? Something that creates the finite or the beginning? Well, science can't tell you. But that's what people, religious people would say, that yes, there's a superpower, something with an infinite mind, that is responsible for creating the universe and you, and everything in the universe. And science cannot dispute that because it doesn't know what happens at time equals 0. There may be speculation or hypothesis or theoretical ideas, but science relies on observation and evidence. Otherwise, it's just a hypothesis. And then you have to take a hypothesis back into the lab, form an experiment to see whether it's true or not, and then have someone else in a different lab corroborate that. So really, you can't go back into the lab and see what happens at time equals 0. You can't create another universe, at least as far as I know. No one has done that and come back to talk about it. So as I say, the religion may have the answer. There's something omnipotent or all-powerful, and something with an infinite mind that's gone on to create everything in the universe and you. And with science, they say at one Planck time, 10 to the minus 43 seconds, the force of gravity separates from the superforce. And at 10 to the minus 35, the strong force separates, and the Earth and the universe goes through a tremendous inflation or expansion, faster than the speed of light. Now the speed of light is constant, so how can something go faster or less than the speed of light? You can look at a planet coming towards you, a planet going away from you, measure the light, and it's the same. 10 to the minus 10 centimeters per second. So what are you talking about? The universe expands faster than the speed of light. Nothing can go through space faster than the speed of light. But space itself can expand faster than the speed of light. Now, it took a while before they got any evidence for that. But they now seem to have that evidence. And also, they figure that the universe was very uniform. The surface, the outside, was very flat or uniform. Like when you blow up a balloon and inflate a balloon, it's very uniform or very flat. At 10 to the minus 12 seconds, a lot of things happen. You can see now that in the first second more things seem to happen than the 13.8 billion years it took to get time equals 0. Yes, did I mention that going back and extrapolating back, figure that it started, what time equals 0? 13.8 billion years ago. At 10 to the minus 12, that's where you get your your electromagnetic force. Electromagnetic force. You also get the fourth force and final force. When you're in that room again, maybe you should be noticed. Because you do radiate. You're a radiant person. Not that much. It would take millions of years times the age of the universe for your protons to radiate away through radioactive decay caused by the weak force. So the weak force is responsible for radioactive decay. And nevertheless, without it you die. The center of the Earth is iron. And the radioactive decay caused by the weak force keeps it molten. And when the Earth rotates every day around its axis, it sets up an electromagnetic field around Earth. That's why you get your magnetic North Pole and your magnetic South Pole. And that protects you from harmful solar radiation coming from the sun and harmful cosmic radiation coming from outer space. It also protects the atmosphere from being blown away by the solar radiation. In the atmosphere, of course, you need that to breathe. And it also mitigates things from outer space coming down and hitting you or causing a great deal of commotion. When I say mitigates, well, it can let some through, but most of them are, the small ones at least, are burnt up in the atmosphere. And the next size is, when they come through, a lot of the material is burnt off, and so they're much smaller, cause less harm. But it can let through some big ones, and it's done that in the past. It caused a great deal of consternation, a great deal of commotion. Figure every 30 million years to get more asteroids coming in, hitting the Earth. Therefore, you can maybe get some bigger ones too, more bigger, larger. Let the force be with you. But at that time, it's when you get your particles. You're made up of particles, your atoms are particles. But for every particle, you get an equal but oppositely charged antiparticle. For an electron, you get a positron. For an up quark, which has a charge of plus 2/3, the anti-up quark would have a charge of minus 2/3. And when you get your particles and antiparticles come together, they annihilate each other, change from matter, from mass, into energy. Now, before 1905, all the scientists said, no, energy and mass are two separate things. Conservation of mass, law of conservation of mass, a law of conservation of energy. And Einstein then said in 1905, no, they're the same, they're equal. Your energy is equal to your mass, it's the amount of material you have, times the speed of light times the speed of light, E equal mc squared. So here again, even if you have all leading scientists have an opinion, it can be wrong, and something can come along, and you have to turf it out. You have a new theory to replace the old. So just because someone says, well, it's scientifically proven, well, be careful, because it could be modified. A new piece of evidence comes along, or a new theory. And for scientific fact, or theory, or law, it has to have all the evidence supported. If you get one piece of evidence, you have to either turf it out, modify it to incorporate it, or say maybe it works, this theory or this law will work under certain circumstances. So how are you here then? Because if there's all particles and antiparticles, you shouldn't be here. Because if you had any antiparticles, you would just blow up. You'd be energy. And here again, science cannot give you the answer. Because in 1 second, they figure for every billion, some say 100 million, antiparticles, there's 1,000,000,001 particle, which goes on to create you and everything else. So why do I say they don't know the answer, why that happens? Because they take it back to the lab and try to convert, and do convert matter into energy. And every time they get an equal amount of particles and antiparticles. So you can't really explain then what happens at time equals 0 and what happens at time equals 1 second. Now at time equals 1/10 or minus 10 to the minus 1, get your protons. So after the first second then, everything is very hot and very dense. It's the fourth state of matter. You have the gas, you have liquid, you have solid, but you have a fourth state called plasma. And everything's so hot and dense there that nothing can combine. You got your photons, particles of light, your electrons, your protons, but only after 380,000 years does it get cold enough or cool enough so that you can get your proton can catch hold of an electron. What do you got then? You have one proton, one electron, hydrogen. That's where you got all of your hydrogen from. And you thought you were just under 100 years old. Well, most of you, at least most of your most of your atoms, 13.8 billion minus 380,000 years old. That's why you got all your hydrogen from. Now, what do we call that theory that I've been talking about? It's called the Big Bang Theory. But back then, there were other theories or other hypotheses as well. According to Hoyle, the universe is steady as you go, the steady state theory. There was no beginning, no end, just was. When he heard about this other newfangled idea that everything seemed to start off with a Big Bang, that's what he said. And he called it derisively, he said, well, that's the theory starts with a Big Bang. So the Big Bang theory was named by someone who didn't believe in the Big Bang theory. But Hubble was proved wrong because of the expansion. The stars going away, and hence the universe contracting, starting at time equals 0. So in order to really call it a true theory, or a law, or a scientific fact, you need evidence. Well, there is a fair bit of evidence for the Big Bang theory, even though they really don't know what time equals 0 and time equals 1 second. How did Hubble know, for instance, that the stars were going away from the Earth? Well, light can be both a particle, a photon, and a wave. To see it's a wave, all you have to do is hold up your two fingers close together, look through with one eye, and you'll see faint lines in between your fingers. Those are caused when light waves interfere with each other. Like you get interference when you throw two rocks in a pool, the waves will interfere with each other. And Newton, back in the 1600s, he said, light can be broken up into different colors, like the colors in the rainbow. The colors in the visible electromagnetic spectrum. Starting from red and going up to indigo. Indigo being like dark purple. And red light, the wavelength is larger than indigo. The wavelength is the length between the crests of the waves. So if the wavelength is larger, it can only go up and down in a given distance less number of times, or less frequently, than indigo light. It can go up and down many more times or more frequency. So red light has less frequency than indigo. Indigo has a higher frequency than red light. Sound is also propagated by waves, so when a train comes towards you, it's pushing the waves together. The wavelengths are smaller, and the frequency is higher, or the pitch is higher. Then the train goes by, it's pulling the sound waves apart. The wavelengths are larger, and the pitch or the frequency is lower. And you hear the train sound go from a high pitch or to a low pitch. Sound drops. Same for light then. When it's going away from you, it's going towards the red. With the larger wavelength and a lower frequency. And when it's coming towards you, it's going towards the indigo with the higher frequency and the smaller wavelength. So looking through an instrument called a spectroscope, you can see that the light from the stars is shifting towards the red. It's called a redshift. Therefore, excuse me, the stars are going away from you. And the light is going away from you, and the stars are going away from you. And then, by inference, going back in time, you come back to time equals 0. Now I mentioned that at time equal 10 to the minus 35, they have gotten that evidence to prove that the universe was expanding faster than the speed of light. At time equal 10 to the minus 12, they do have, they can simulate that back in a lab. Cool enough, they can have a machine that has that kind of energy. It's called a Large Hadron Collider. Hadron is anything with mass. It's the largest one is located in CERN is located in Switzerland. It's an underground tunnel, a loop of some 27 or so miles or kilometers long, containing large superconductors, big magnets, so you can accelerate particles in one direction near the speed of light, and particles in the other direction in the speed of light, near the speed of light, collide them and see what they're made out of, like in a car roller derby, when the cars collide, the parts fly off, so you can see what the cars are made of. At first, there were so many particles, they called it a particle zoo. But then they narrowed it down and came up with a particle theory, which really explains everything about everything, all your particles and all your forces in the universe. You, as I said before, are up and down quarks. There are two other pairs of quarks, charm and strange. Scientists do have a sense of humor. And top and bottom. And for each one of the pairs of those quarks, there's another particle called a lepton. For you, your lepton is an electron. So you do have other things, but because you're up, besides your up and down quarks, you have quite a few electrons. For the other two pairs of forces, it's the tau and the mu, or the muon. Then you have the four forces: the electromagnetic force, the strong force, the weak force, and the force of gravity. But for each of those forces, there's another particle called a boson, and it's the interchange of those bosons that give you the force. For instance, the electromagnetic force, the boson is a photon. So when you hold two magnets, south poles, magnets together, or north poles, try to, and they resist coming together, what's happened is the exchange of light, exchange of photons, keeping them apart. For the strong force, we call that's the force that keeps you from flying apart, keeps your nucleus together. It's called the gluon. And for the weak force, it's actually two, W and Z, not Z but Z. And for the force of gravity, it's a graviton. Now, the collider couldn't find a graviton. You need a collider the size of the solar system to do that. But just don't have enough energy to get the graviton. But there's another place recently, the last decade or so, that did find a graviton. Because it's called the LIGO, L-I-G-O, Laser Interferometer Gravitational Observatory, LIGO. And as the name suggests, it finds waves, and it found gravitational waves, and therefore there must be a graviton. And whenever you predict something, and it comes true, it gives more credence to your theory or your hypothesis. They also figured, though, they needed another boson, a fifth boson, to give mass to the other particles. A guy called Higgs. He proposed that back in the 20th century. And in 2012, when they gave the Logic Hadron Collider at CERN more power, more energy, they found it in 2012. So they now call it a Higgs boson in his honor. And when they found it, all the particle physicists jumped up and down with glee. Again, if something is predicted and then it's found or proven to be true, it gives more credence to the theory. So that explains really all the different particle forces in the universe and you. So that's another piece of evidence then for the Big Bang theory. Another one is a light. Up to 380,000 years after the Big Bang, light was trapped in the plasma, photons of light. And then at 380,000 years, a photon of light escaped. And you're still being hit by that. It's not part of the visible spectrum, it's the microwave. And we see it's the lowest part of the electromagnetic spectrum, the same as visible light. Microwave we don't see, can't see unless you're a bee. A bee can see it in the range. So 3% of the static that you get in your AM radio is caused by microwave background radiation. And 3% you got in your old TVs with an aerial is also. It's very cold. It's cooled down. And it is 3 degrees above absolute zero. Absolute zero is the coldest anything can get. It's 273 degrees centigrade. So your microwave background radiation would be 270 degrees below zero. Discovered that really by accident. Bell Labs back in the mid 20th century made a big receiver as tall as a 2-story house. And wherever they pointed it in the sky, they got this static. Couldn't figure out why. I mean, they thought maybe a bird dropping, so they washed it out and so on. No, they still got the static. It remained for the theoretical particle physicists to explain why. It's a remnant of the Big Bang radiation. And even Gamow, he predicted what it would the temperature would be, and he was very close. So that's another piece of evidence that supports the Big Bang theory.